The spontaneous routes of nuclear decay, along with nuclear fission and nuclear fusion, going to be the topics of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. I'll leave a link in the description below for where you can find those courses. Now, this lesson is part of my new general chemistry playlist, and for at least a couple more weeks, I'll be releasing several lessons a week throughout the school year. So if you want to be notified every time I post a new one, or when I post my next playlist, subscribe to the channel, click the bell notification. All right, so we're going to start with spontaneous routes of nuclear decay here. And these are things we observe in nature. They happen spontaneously. And at the end of this lesson, we'll briefly talk about nuclear fission and nuclear fusion. So for our spontaneous routes of nuclear decay, there are 5 of them: alpha decay, beta decay, positron emission, electron capture, and gamma decay. So alpha decay might also be called alpha emission. It involves the emission of an alpha particle. Beta decay might also be called beta emission. It involves the emission of a beta particle. Positron emission is just called positron emission. Electron capture, though, does not involve the emission of anything. It's where an inner core electron actually gets sucked into the nucleus, not ejected out of it. And then finally, gamma decay could also be called gamma emission, and where a gamma ray is emitted from the nucleus. So 4 out of the 5 are emissions. Electron capture is the only one that is not an emission. We'll see what that looks like from balancing the reaction and looking at the reaction perspective. All right, so alpha decay, again, is where an alpha particle is going to be ejected out of the nucleus. And so when an alpha particle is ejected out of the nucleus, that means you're going to have an alpha particle as a product in that nuclear reaction. So let's say we take a look at an example here of each one of these happening to, say, uranium-235. And so if we take a look, what would alpha decay look like? Well, if I start with uranium-235, and the question was, predict the product of alpha emission or alpha decay of uranium-235. Well, I'd start with uranium-235, and then I would eject out that alpha particle, an alpha particle as a product, and then I'd see what I have left on the product side here. And so in this case, we got to get that mass number, 235 on the reactant side, so 4 plus a total of 231. So there's our mass number. And then 92, well, 2 plus 90. So an atomic number 90 happens to correspond to thorium. And so if the question is, what's the product of the alpha emission of uranium-235? It would be thorium-231, as we just figured out. So alpha emission, again, always involves the emission of an alpha particle. So it's going to be on the product side in every case. Now, what you need to know about this is that this actually reduces the mass number. And the reason that's important is because it's the only one that does. All the rest of these don't affect the mass number of a nuclide at all. So why in the world would you want to reduce the mass number? Well, if you recall, when we talked about trends in radioactivity, we said that atomic number, all the atomic numbers bigger than 84, they're all radioactive, or bigger than 83, 84 and up, they're all radioactive. So and the larger you are, the more likely you're going to be radioactive. Heavy elements just tend to be radioactive. The only way they can reduce their mass number and get lighter, so to speak, is alpha decay. And so alpha decay becomes really prominent among heavy elements. All right, so let's talk about beta decay. So in beta decay, rather than having the emission of an alpha particle, you're going to have the emission of a beta particle. And so in this case, it's always going to be that electron, if you will. So ejecting an electron, but again, more proper to call it a beta particle when it's being emitted out of the nucleus. So it's always going to be on that product side yet again. So if we wanted to say, well, what's the product of beta decay of uranium-235? Well, then we'd be writing a beta particle as our product. And then again, asking ourselves, what's that mystery particle left? So balance the mass numbers yet again, and we can see the mass number over here has to be 235 as well. 0 plus 235 equals 235. But we can see that the atomic number needs to be number 93, as 93 plus -1 equals 92. And if we take a look on the periodic table, atomic number 93 corresponds to neptunium. And so what's the product of beta decay of uranium-235? Neptunium-235. So let's take a little deeper look at what's going on here. So if we take a look at uranium-235, atomic number 92, reminder just means it has 92 protons. So and if you take the difference, 235 minus 92, you get the neutrons. So we got 143 neutrons. So, and then over there at neptunium, so atomic number 93 means we got 93 protons, and then 235 minus 93 is going to get you 142 neutrons. And we can now kind of see what's going on. So in converting uranium-235 to neptunium-235, the atomic number went up by 1. We gained a proton, but the mass number stayed the same. So to make room for that proton, we must have lost a neutron. So if you gain a proton and you lost a neutron, functionally beta decay actually converts a neutron into a proton. That's what it actually accomplishes. So and if you kind of take a look at it like this, so if you take a proton, which is +1, and an electron, which is -1, and sandwich them together to form a single particle, well, it would now have no overall charge. So, but a proton weighs 1 AMU, an electron weighs close to 0 AMUs, and so sandwich them together, you get something that essentially weighs close to 1 AMU still. So no charge weighs close to 1 AMU, that's a neutron. And so if you take this neutron that you might think of as being functionally equivalent to a proton-electron combination, and you eject away that electron, well, what do you have left behind? Well, you have a proton. And so that's why when you eject out that beta particle, you've functionally in that nucleus converted a neutron into a proton. All right, and that's worth knowing. So why in the world would you want to convert a neutron into a proton? Well, for one very important reason. You have too many neutrons and you don't have enough protons. And the evidence of that in terminology we've seen before is that your N/Z ratio is too high. So we said in the first lesson in this chapter that for the elements up through atomic number 20, up through calcium, they wanted an N/Z ratio exactly equal to 1. Well, what if their N/Z ratio was greater than 1? Well, then they'd be a good candidate for beta decay, because turning neutrons into protons lowers your N/Z ratio, getting it back closer to 1. We can also look at this in terms of that belt of stability we saw in that first lesson as well, where we plotted N versus Z, and we saw that all the elements fit right on this narrow region along what we call the belt of stability. All the stable nuclei, all the stable isotopes are right along there. Well, if you're up here, you have too much N and not enough Z, and that's where you're likely to undergo beta decay. Your N/Z is too high. So cool, on that left side, above the belt, so to speak, that's where you're likely to do beta decay. All right, so let's take a look at positron emission here. In positron emission, instead of ejecting out an electron, you're going to eject out a positron, which again has a +1 charge instead of a -1 charge. All right, so what's this going to look like? Well, now we can rewrite this. And instead of -1 here, we're going to have +1 for the charge. And so what's this mystery particle we get as a product? Well, in this case, again, 0 plus 235 is going to equal 235, so we're going to have a mass number of 235. And then 1 plus what equals 92? Well, 1 plus 91. So, and in this case, who's atomic number 91? Well, that is protactinium. Cool, and so we see that the positron emission of uranium-235 results in protactinium-235. Well, and once again, if we go back and count up the protons and neutrons, we can kind of see what's going on. So in this case, we go from 92 protons to 91 protons, and we go from, again, 143 neutrons to 144 neutrons if you take that difference. And so all of a sudden now we're losing a proton and gaining a neutron. We're doing the exact opposite. And this makes sense. If you're ejecting out a negative electron, it should have one effect. But if you're ejecting out a positively charged electron, a positron, it should have exactly the opposite effect. And so here we're now converting a proton into a neutron rather than a neutron into a proton. Cool, and you should definitely know that, that's what positron emission accomplishes. It converts a proton into a neutron. Now, why would you want to do that? Well, again, for one reason. You've got too many protons and you don't have enough neutrons. And what's the evidence of that? Well, that again goes back to your N/Z ratio here. Your N/Z ratio is now too low rather than too high. And so it turns out if you're over here, below the belt of stability, that's where positron emission might become likely. But we'll find out that positron emission is not the only candidate there, Because we're about to find out that electron capture functionally accomplished the same thing. Electron capture is also going to convert a proton into a neutron. They both lead to the same result. So, but in electron capture, rather than having any particle as a product, you actually have an electron as a reactant in that reaction instead. So if we go back and take one more look here, so at our uranium-235, you know what, it's not right there. Let's leave our space. So uranium-235, and now we're going to add an electron to it on the reactant side. And the question is, what's our mystery particle now? Well, we can see that 235 plus 0 has to give us a mass number of 235. And then 92 and -1 is 91, so atomic number 91. And once again, we see we've got protactinium 235 resulting exactly as we did before. Cool, and if we work it out, we'll see, yep, we've definitely lost a proton and gained a neutron, and so we've functionally converted a proton into a neutron. And why would you do this again? So, well, again, you do this because your N/Z ratio is too low. And so how do you distinguish between these two? How do you know which one happens? Well, you won't always know, but there's one big major difference here, and that's if you're heavy or light. It turns out electron capture is only likely in heavy elements, so whereas positron emission is much more likely in lighter elements. And so if you're down here in the lighter elements, positron emission is more likely, but if you're up here with the heavier elements, then electron capture is more likely. Notice in both cases, your N/Z ratio is too low. You're below that belt of stability. It's just, are you below that belt of stability and light, positron emission? Below that belt of stability and heavy, electron capture. All right, finally we've got gamma decay, and gamma decay is kind of the easiest one to deal with. So it's gamma emission, so you've got a particle or ray in this case as a product, not a reactant. And in this case, this one's kind of the easiest to deal with. It's the only one, again, we're not dealing with a particle, we're dealing with electromagnetic radiation. And you're just giving off really high energy light, but it doesn't change the nucleus at all. Again, this has no mass number, no atomic number. So your original nucleus, which sometimes we call the parent nucleus, and your product nucleus, sometimes we call the daughter nucleus, are one and the same. So again, if we did this with uranium-235, we'd see that we still have to have this be uranium-235. There's no difference. So, and it turns out you can kind of think of this as a nucleus in an excited state dropping down to a lower energy state. We saw this with electrons. We saw electrons in the excited state, and when they dropped down to the ground state, let's say, they emitted light. Well, same kind of thing here. You have a nucleus now in some sort of excited state, dropping down maybe the ground state or maybe just some lower energy state, and it's giving off light in the process, but the difference in energy here is a much larger difference than we saw with electrons, and as a result, we're giving off much higher energy light. Now, this is the one with gamma decay that we're not going to have you predict when this happens. It turns out this never happens by itself. It usually accompanies one of these other processes happening first, but not something we can do in any sort of predictive way. All right, so let's get that back off here. Okay, so you should be able to predict products associated with any one of these. You should understand if the particle's on the product side or on the reactant side. You also might have to, actually predict which of these a specific nuclide might do. Now, we kind of looked at, well, if you know where it's located on, on the belt of stability, you know which side of the belt, above the belt or below the belt, what it might do and stuff like this. However, I might just give you a nuclide and have you figure it out based on some things you know. So let's say I gave you fluorine-20. So fluorine-20. And I said, what is the most likely route for nuclear decay, if any, for fluorine-20? Well, fluorine-20, fluorine's atomic number 9. And so we're dealing with a light element, and that makes it a little easier. So in this case, alpha decay is probably not so likely. Atomic number here is not bigger than 83. So then what are we going to do? Well, let's look at that N/Z ratio. And we can see here that the number of protons, again, is 9. The number of neutrons, 20 minus 9, is 11. And so we can see here that our N/Z ratio is definitely not equal to 1. In fact, it's greater than 1. And if it's greater than 1, then we are above the belt of stability here. And if you're above the belt of stability, Only likely candidate in this case for a light element, since we ruled out alpha decay, is going to be beta decay. So, and that's what your answer would be. What's the most likely route of radioactive decay? For fluorine-20, beta decay. But now we can also see why, because if we do beta decay, we'll eject or emit a beta particle, and then the question is, what do you have left? Well, in this case, 0 plus what equals 20? Well, 0 plus 20 equals 20, and then negative 1 plus what equals 9? Well, negative 1 plus 10 equals 9. And who's atomic number 10? Well, that's neon. And all of a sudden, you look and you say, okay, well, now we've got 10 protons, and then 20 minus 10, you also have 10 neutrons, and now your N/Z ratio is exactly 1, and you've got a stable nucleus. And so that's kind of the idea. So when you're above the belt of stability, the way you get closer to that belt and lower your N/Z ratio is beta decay. If you're below the belt of stability, how do you raise your N/Z ratio and get closer to that belt of stability? Well, you either do electron capture if you're heavy, or you do positron emission if you're light. So that's kind of the idea here. So if you're having for a specific nuclide to predict what kind of route of spontaneous decay it's likely to go, odds are you should be calculating the N/Z ratio and seeing if it's too high or too low. So to finish off this lesson, we just got to briefly talk about fission and fusion. And first got to talk about what these words mean. So nuclear fission versus nuclear fusion. So we'll start with fusion, actually. So in fusing things together, you're bringing things together and kind of binding them together. And that actually is what happens in a nuclear fusion reaction. In a nuclear fusion reaction, you're taking two lighter nuclei and combining them together to form a heavier nucleus. Now, fission is the opposite. So if you think of like a fissure, it's like a crack or a crevice here, and you're breaking things apart, so to speak, and that's what happens in a fission reaction. You're taking now a large nucleus and breaking it apart into smaller nuclei instead. All right, so it turns out that heavier nuclei are much more likely to undergo nuclear fission, lighter nuclei are much more likely to go nuclear fusion. And it turns out we actually know where the boundary between heavier nuclei and lighter nuclei lie, and that turns out it's iron 56. So that's the specific isotope, and it turns out that iron 56 is the most stable nucleus in existence. And if you're heavier than iron 56, well, then you're going to try and break apart so that you can get lighter. And so elements that have a mass number greater than 56 tend to undergo nuclear fusion rather than nuclear fusion if they're going to go one versus the other. Now, on the other side, if you're lighter than a mass number of 56, you're much more likely to undergo nuclear fusion than nuclear fission so that you can combine to get heavier and get closer to 56. So that's kind of the idea. All right, so fission versus fusion. If you look at nuclear fission, so this is most commonly, when you think of nuclear reactions, you're most commonly probably thinking of nuclear fission. If I say, name for me an element involved in nuclear reactions, you're probably going to say something like uranium or plutonium. And those are heavy elements, and they're undergoing nuclear fission. So in fact, all of our nuclear reactors up till now in 2022, anyways, they are nuclear fission reactors. So, and they all involve heavy elements getting split apart into lighter elements with the release of a ton of energy in the process. So, but we got to go and mine things like uranium and plutonium in order to do these things. And they also form things that tend to themselves be radioactive, and so they produce a lot of radioactive waste. Now, they do produce a lot of energy, so comparatively speaking and stuff like this. But again, there's some problems here. Now, nuclear fusion, on the other hand, involves light elements. Like in this case, I've got an example with deuterium and tritium, which are both heavy forms of hydrogen. So, and they're combining here to form a helium nucleus. So now where might you find this happening? Well, most prominently, you're probably finding this happening at the core of a star. So nuclear fusion happens at the core of a star. It also produces a ton of energy, and that is the energy being given off by our sun, for example, or by other stars. It is this nuclear fusion process happening at the core of a star that produces all that energy. So it's also where we get all the elements from. So you're going to keep combining lighter and lighter elements to produce heavier and heavier elements. So in things of this sort, you take a look at our sun, and our sun is made of mostly hydrogen, like 75% hydrogen, 25% helium, and those are approximate because there's trace amounts of all the rest of the, a lot of the rest of the heavier elements and stuff. But it's mostly just hydrogen and helium with small amounts of some of those other heavier elements that have all been made in this kind of nuclear fusion process. Now, a couple things here. So this nuclear fusion process only can occur, as we know it up till now, at really, really, really high temperatures, like those you'd find at the center of the sun. So like millions of degrees Celsius. Whereas nuclear fission, that can happen at room temperature. And usually, in fact, usually we try to keep it not, for, because it's giving off energy, it usually heats things up, but we don't want it to get too hot, limit the reaction and stuff, or else we might have a nuclear meltdown or something like this. So we try to keep it from getting hot. But this can happen at room temperature. But nuclear fusion requires millions of degrees and is a little bit of a pain in the butt. And so how do you build a container in which to do nuclear fusion that won't melt if it gets to millions of degrees and things of the sort? But obviously nuclear fusion is an active form of research though, because the truth is the fuel for this is hydrogen. And we have lots of hydrogen all through the oceans in the form of water, right? And we can get that hydrogen out of the water, and then we could have it undergo nuclear fusion and create lots of cheap, abundant energy, which is really a secret to life on this planet, or at least modern life as we know it. And again, we can get lots of energy from fission, but it's not like I just go get a bunch of hydrogen out of the ocean. I've got to mine uranium and mine plutonium, dirty processes. And then, the waste products are going to be dirty themselves, and we have to store those. And so if we could do nuclear fusion, this would be a win-win-win-win-win for humanity. But it is a little bit of a problem. Now, in addition to the core of stars, there is one other place where you might encounter nuclear fusion, and that is with an H-bomb. So now there are nuclear bombs, and nuclear bombs are fission bombs, and they require heavy elements and things of the sort. But there are also fusion bombs that most commonly you'll hear called an H-bomb. And so what's the difference? Well, here's the deal. Your fusion bomb still has nuclear fusion, which means before that bomb can go off, the bomb has to get heated up to millions of degrees, because that's the requirement for nuclear fusion as we currently know it. So how do you heat up the bomb to millions of degrees? Well, the way you do this is you take that H-bomb and you hook up a fission bomb to it to use as a detonator. That nuclear fission bomb, your nuclear bomb, goes off, heats up the other bomb, and then that bomb goes off with an even bigger payload. So the moral of the story here is that if your detonator is a nuclear bomb, then you got a really, really big bomb in your H-bomb there. But that is fission and fusion. And again, you kind of understand the difference between the two in terms of breaking apart heavy nuclei or combining lighter nuclei. You should know that iron 56 is kind of the boundary in between. If you're bigger than that, you do fission. If you're lighter than that, you'll do fusion. And that's about the gist of it. Now, if you found this lesson helpful, a like and a comment letting me know are pretty much the best things you can do to support the channel. And if you are looking for general chemistry practice, if you are prepping for finals and looking for final exam rapid reviews and practice final exams, then take a look at my general chemistry master course. I'll leave a link in the description below. Free trials available. Happy studying.